Hi, everyone. Just wanted to take a minute to talk about biconditional statements. Um, I'm not going to spend a whole lot of time on these, but they are important to know for your future math careers. And ultimately, they're the scenario where we are talking about um, both P implies Q and Q implies P. So a biconditional, it's just a combination of P implies Q and the converse Q implies P. So resulting in P if and only if Q. And basically, what we're saying by this is if this is true, it means that P implies Q, that is true, and that Q implies P is also true. All right, that is our goal to illustrate for the biconditional statements. Um, you can see over here as well that if they're both false, then it technically is true, but we're not going to spend a lot of time on that one. These two cases in the middle here, that's talking about saying like if P implies Q is true, but Q implies P is true, we can't write it as a biconditional. I mean, it's false. Sorry, if this one was false, we couldn't write this as a biconditional. This one was true, but that one was false. We could not write it as a biconditional. All right. So, in terms of what we are dealing with here, we're dealing with if and only if. So, P if and only if Q. A way you can abbreviate that is IFF. So, if you ever see that notation, that just means if and only if. And it just is illustrating a biconditional. And when we are dealing with these in the couple instances we are in this year, I know you're going to love them because it essentially is saying we have two proofs for the price of one. All right, so let's look at a quick example. This is kind of a real world little example, and it kind of shows you how specific you do have to be with the biconditional statements. So if we're dealing with a marine biologist writing about seahorses, we're saying if a seahorse gives birth, then it is male. Since it is true that among seahorses, only males become pregnant and give birth, the marine biologist states, can she state this as a biconditional? So obviously we did just say that the conditional itself is true. So we do have to look at the converse. If a seahorse is male, then it gives birth, which is false. Because we would need to find a counterexample, and that would just take us finding a male seahorse that has not given birth. All right. So we actually, even though this seems like it should be relatively straightforward, cannot write this as a biconditional. Let's look at another quick example. What are the two conditionals implied by the biconditional? So you do need to be a little bit careful with these for the sheer fact that you'll notice here that even though the word triangle comes up only once, right, we have triangle and triangle here, just because the triangle is kind of applying to both, right? You have to look and make sure the sentences in of themselves make sense with part of it. So like if I just said a triangle is equilateral, and then I said has three congruent sides, well, what's the it? The triangle. The triangle has three congruent sides. So ultimately, if we were to look at this, we could write this as P implies Q. If a triangle is equilateral, then it has three congruent sides. That's true. If a triangle has three congruent sides, then it is equilateral. That is also true. That is the definition of equilateral. So this actually could be written and used as a biconditional where this is true. All right. So what are the two conditionals implied by this biconditional? So let's look at them real quick. The product of two numbers is negative if and only if the numbers have opposite signs. All right. So let's identify P and Q. We have the product of two numbers. Whoa, numbers. Neg is negative. The numbers, you could say two numbers, by the way. Numbers have opposite signs. Okay. So the product of two numbers is negative, and the two numbers have opposite signs. So if you were to write this, the two conditionals, right? P implies Q if the product of two negative two numbers is negative, then opposite signs, right? Which I'll let you think about in terms of whether or not that is true or false. And then finally, if we did the other way, if two numbers have opposite signs, whoa, then negative product. All right. I'm just using some shorthand. You could write it all out. But ultimately, what we're doing is we're looking at P and Q and we're rewriting them as a conditional and its converse. Okay. So let's just do a quick recap of everything we've covered. Oh, no, wait, one more. We have one more example. Write it as a conditional, and then we're going to determine the truth value. So again, let's do one quick more. All right, well, if we were to write, I'm sorry, we're writing it as a biconditional. We're already given the conditional here. So the other way would be, right? So if two lines are perpendicular, then they intersect at right angles. Okay. So if two lines intersect at right angles, they are perpendicular, and if two lines are perpendicular, then they intersect at right angles. So I'll leave you to think about whether or not those are both true, false, or one and one. But ultimately, if we then were to combine them together, we would get the statement two lines intersect at right angles if and only if, I'm just writing it out that way, they are perpendicular. All right. So that would be ultimately how you write that as a biconditional. All right, now for real, let's look at the summary. So this is a quick reminder. The conditional, P implies Q. A converse, Q implies P. Inverse, not P implies not Q. Contrapositive, not Q implies not P. And then the biconditional is P if and only if Q. And their truth values, again, the conditional and the contrapositive are equivalent truth-wise. Converse and inverse are equivalent truth-wise. And the biconditional, we're really only going to be looking at situations where both the conditional and the converse are true. All right, have a great day.